Greetings Year 11 students to another exciting class involving exponentials and logarithms. So let's have a look now at some of the graphs that we can produce. What we need to understand that the word exponent means index or power. So y equals a to the power of x is called an exponential function. It's because it's involving the exponent or the index or the power is up here, a to the power of x. If we actually want to write y equals log to base a of x, that's called a logarithmic function. We can graph exponential functions and logarithmic functions. And the interesting thing is, and we can see this example here, that when we graph an exponential, these power ones, they will always take this shape here. They will have the x-axis as an asymptote. And they'll always get bigger and bigger and bigger as you go further out. If you draw a log graph, they'll have the y-axis as an asymptote, and they'll get smaller and smaller and smaller as you go out, still increasing. But those two graphs will be a perfect mirror reflection across the line y equals x. Now if you look at the first exponential graph, that y equals 2 to the power of x, it goes from left to right. All x values are real, so it has a domain of all real x. The range is all y values must be greater than 0 because the x-axis is an asymptote. And it's getting bigger, it's increasing. And as it's increasing, it's getting steeper and steeper. It's increasing at a faster and faster rate all of the time. The shape is called concave up. That's what you call it when the gradient is increasing as you go across. For the log graph, it can take only positive values of x because the y-axis is an asymptote. It can take any value of y because it goes up forever and down forever. It's actually increasing, but it's increasing at a slower and slower rate, and when that happens, it's called concave down. So we need to understand that they're a perfect reflection across the line y equals x, and if they are a reflection across the line y equals x, they're called inverse functions. And we've also covered this one before because we know that logarithms with a power s, a to the power of log to base a of x equals x, we've covered that before. So let's get into actually trying to sketch a graph. So first thing we need to do is come up with a set of axes. So I'm going to sketch them both on the same graph, I think. So here is my x-axis and my y-axis. Sketch 3 to the power of x. Now if I sketch 3 to the power of x, I know this. It's like that. I need to be careful. I can't allow that to look like it's starting to hook up because it's approaching the x-axis. So that's y equals 3 to the power of x. Now what I'm actually going to do, and you can think about this, I'll write it here, but you can think about this. I want to just get at least 2 points. I know the basic shape. When x is 0, 3 to the power of 0, anything to the power of 0 is 1, so it goes through there at 1. When x is 1, 3 to the power of 1 is 3, so it goes through here at 1, 3. I have a horizontal axis, and that's the line y equals 0. I shouldn't say horizontal axis, a horizontal asymptote. And the horizontal asymptote is the line y equals 0, so I can see that that's an asymptote there. So for y equals 3 to the power of x, the domain is all real x because it goes to the left and right forever, and the range will be y values must be greater than 0. They can't be 0 because the x-axis is an asymptote. Now, for the second graph, y equals 3 to the power of minus x, I know it's going to be like 3 to the power of x, but manipulated somehow. So this is what I'm actually thinking. Come over here, just try a value or two. 3 to the power of minus 0 is 3 to the power of 0, which is 1, so it goes through at 1. 3 to the power of minus 1 is actually 1/3, which means I go out 1 and down 1/3. If I tried minus 1, 3 to the power of minus 1 is 3 to the power of plus 1, which is 3. So I would get that there, which means my graph will look like this. And that's y equals 3 to the power of minus x. Now, it has also a horizontal asymptote of y equals 0. For y equals 3 to the power of minus x, the domain is also all real x, and the range is also y greater than 0. Same domain and range as y equals 3 to the power of positive x. When we go to our second example, I have a slightly different scenario. Now I know what y equals 3 to the power of x looks like, so I can really quickly sketch that one. I have a horizontal asymptote. That is the line y equals 0. I'm going through at 1, and we said that was the point 1, 3. You must have the y-intercept shown and at least one other point to give it a sense of its shape. Now, let's get the second one. If I'm doing y equals minus 3 to the power of x, just a couple of points might be required here. Let's try 0. Becomes minus 3 to the power of 0. Anything to the power of 0 is 1, so it's minus 1. Let's try 1. Becomes minus 3 to the power of 1, which is minus 3. I don't think I need any more. I'm going to go to 0, minus 1. I'm going to go to 1, minus 3. And I know it's the same type of graph, but it's like that now. So it's 1, minus 3. Has the same horizontal asymptote, but when I look at their domain and their range now, so for y equals 3 to the x, we know that the domain was all real x, and the range was y greater than 0. For y equals minus 3 to the power of x, the domain is all real x, and the range is y is less than 0 because it's under the x-axis. So, playing around with our graphs. Let's sketch a log graph. Okay, so same process. I know the basic shape of a log graph. I could use a table of values. I don't want to use that. I know log graphs go like this. Now, if I'm graphing y equals log to base 2 of x, if I plug in, oops, let's do that slightly differently. I'll go like this. If I plug in 1, log to base 2 of 1, you can do on your calculator log 1 over log 2, or you can say what power do you put above a 2 to get an answer of 1, and it's a 0. And it means it goes through, and they always go through 1. Log to base 2 of 2, what power do you put above 2 to get 2? It's going to be 1. You can do it on your calculator using your change of base law if you want to, and that means that that's at 2, 1. I have a vertical asymptote, and that's the line x equals 0. Now let's state the domain and the range. So for y equals log to base 2 of x, the domain is x is greater than 0. It's all positive. It's to the right of the y-axis. The range, all real y. So now let's consider the log to base 2 of x take 1. That's a bit trickier. So y equals the log to base 2 of x take 1. Now brackets normally control left and right movement. I wonder if that's going to do the same thing. So let's just do a bit of a quick check. If I use 1, I can go to the question. I go the log to base 2 of 1 take 1, the log to base 2 of 0. That does not work. So let's try 2. And let's try 3. So if I let x equal 2, 2 take 1 is 1, log to base 2 of 1, we know the log to base 2 of 1 is 0. I know that because I did it up here. The log to base, if I let x equal 3, 3 take 1 is 2, the log to base 2 of 2 is 1. Which means now, don't worry about that one, that doesn't make sense. If I go to x equals 2, and y 0, if I go out to x equals 3, y equals 1, my asymptote is now x equals 1. Look at the bracket. If you let x equal 1, 1 take 1 is 0. The asymptote becomes the line x equals 1, which means my graph will look like this. It's exactly the same as the blue graph, it's just pushed across 1 unit to the right. So the bracket did control left and right movement. So y equals the log to base 2 of x take 1. The domain is x is greater than 1, and the range is all real y. It goes up and down forever. So there's our sketch. Another one. Let's see what happens. Log to base 2 of x. Well, we know what that looks like, so I can do a really quick sketch of it. Log to base 2 of x, something like that. Goes through at 1, goes through at 2, 1. We've just done that graph, so we know what that looks like. Oops, I don't want an x there. I want a x here. Vertical asymptote is the line x equals 0. There's my y-axis. Okay, now, what is the effect of the plus 4? Well, that means it's just going to push my graph up 4 units. So what, log to base 2 of x plus 4. So this point here will be up 4. This point here, across 2 up 1, will be up 4. So it'll become across 2 up 5. And my graph will go something like this. Still has the same horizontal asymptote. So for y equals log to base 2 of x, the domain is x is to the right of 0. The range, all real y, because go up and down forever and it must be to the right of the y-axis. But for my green graph, the domain, x is greater than 0 as well. range or real y? Is it possible to find out where it crosses the x-axis? How do you find an x-intercept? You let y equal 0. So for that particular graph, I will try that. So if I go y equals 4 plus log to base 2 of x, if I let y equal 0, move the 4 across to the other side. Let's play sliding bases, so changing it from logarithm form to index form. 2 to the power of 4 is 16, so 2 to the power of minus 4 is 1 over 16. So that's the point. 1 over 16 comma 0 there. So you can find the x-intercept if you want to. Time for you to try some questions. Enjoy the graphical experience that you've got to look forward to. Bye for now.